And don't delete it accidentally. I do that sometimes too. All right. So last time we got to this point, and I wanted to talk a little bit about how much of the error is explained by the least squares model that we find. So we talked last time a little bit about finding the total sum of squares and the regression sum of squares and the error sum of squares. I want to make sure that I go back through this again because, like I said, I think I was messing it up last time, which is why I just decided to start it over again today. So when we're talking about error, remember the x, the least squares solution that we find, this x, isn't the exact solution to the system that we started with. Right? Typically. If it is, that meant that everything was on that perfect linear whatever it happens to be, either a line or a plane or what have you, whatever you're trying to graph. If it was exactly a solution where the error is 0, then you fell directly on that line, if you're doing like a regression line, or if you're doing a plane or what have you, whatever it happens to be. If you're doing a regression quadratic, any of those kinds of things. If it happens to lie exactly on there, then the error would be 0 no matter what you plugged in for x, right? But in general, there's going to be some sort of an error between the solution that we have and the problems that we were, the points that we were given. So if I let E be the error, I can express E as B minus this AX. X, I'm using X here to actually refer to the least squares solution. So that X is the least squares solution. If I replace what X is, well, X is A transpose A inverse times A transpose times B. Oops. Nope, that was right the first time. This is just taking out the X and putting in what X is equal to, the least squares solution. Notice that I've got a B on both sides, right? Or in both terms, I mean. So I can factor out that B on the right, and I'm left with the identity matrix minus A times A transpose A inverse times A transpose.
Does it matter if the B is on the right or the left?
It does. It needs to be on the right. It needs to be on the right because it's on the right of that second piece. Matrix multiplication, it matters what side you're on, so it has to be on the right. We're going to come back to the form of this matrix here in a minute, and it's going to relate back to stuff that we talked about before Easter. But what we're interested in doing here is trying to basically split up our y's into an explained piece and an unexplained piece. What I mean is we've got some error that's explained by the model, and then some error that's not explained by the model. That's our goal here. To that end, I want to try to break up things, if I can, into pieces that are orthogonal to each other. So if I multiply through here by A transpose, multiply both sides by A transpose here, notice that it hits this piece here, and I can distribute the A transpose through. So you would have A transpose minus A transpose A times A transpose A inverse times A transpose times B. It's a lot of A's and A's transposes. However, what does that thing inside the parentheses simplify to? Yeah, so inside the whole parentheses, it goes all the way down to what was it? 0, right? Notice I've got A transpose A and its inverse. Those cancel each other out. It becomes the identity, right? And then we've got A transpose minus A transpose. We just get 0. So we get that A transpose times E here is 0, the 0 matrix. Yeah, it's actually the 0 vector.
The E vector is just the actual y minus the model y.
Yes, it's the actual y minus the model y. Yep. Yep. That's right. All right. So if we let's call it y hat, let's let that be our ax, then we notice that our b, those were our solutions, those are our actual y's, right, is equal to the y hat plus the error. And in particular, we have that the y hat here and the error term are orthogonal to each other. Because if I did the dot product of them together, I would get 0 in this case, because we can do dot product with doing transposes in particular. So if for example, if I wanted to do the y hat dotted with the e, if you think about how dot products work, remember we match row to column? So that would be the same thing as y transpose, make it a row vector, times the column vector. Oops, just make it actual honest to goodness matrix multiplication. This would be the x transpose A transpose E, because that would be the transpose of AX. Y hat is the same thing as AX. And what did we just say that A transpose E was equal to? 0, right? So this would actually be, honest to goodness, 0 here. Okay. So the y hat and the error term here are orthogonal. Now remember how we started all this stuff with least squares. We talked about the set of solutions, if you will, to the column space of A. So say we did all the linear combinations of the column space. That's that plane thing that I drew. We've got our B vector that comes out. And we're trying to do basically projection down. So this part right here where we project the B down into the plane, that's our y hat. And the part here would be your error, the difference between the two. That would be E. That's geometrically what's going on.
But if y hat is defined as just A times the X matrix, wouldn't that just be the B?
The X matrix isn't the B. The X matrix is the A transpose A inverse times A transpose minus B. It's the least square. So I'm using X for the least square solution.
Okay.
Yeah. Yeah.
So what would the y hat represent?
The y hat's just representing the A times the least square solution. Yeah. I probably should have used a different letter than the X, but I'd already used it. That was what I used to get to the least square solution. So. All right. Yeah, I'm not using X as a variable now. I'm using the actual honest to goodness solution, the least square solution. Okay? So again, geometrically, the idea is to take the vector B and project it down into the space that's generated by the columns of A. We're going to do this again in another setup with a set of functions with a different dot product, but the idea is the same. We'll do this in a little bit here when we talk about Fourier series. It's going to be the same kind of setup, just with a different dot product and a different idea of orthogonality. All right. So anyway, the important part here is that we really do have a right triangle type of relationship. So if I want to know things about the relative sizes, Pythagorean theorem would hold here, for example. Okay. All right. Anyway, so we have that these two things are orthogonal. We'll get back to that as well. There's the black. So going back up here again then, for our B, there is the y hat. This is the explained part. And then plus the error, which is the residual part. All right, so going back to what we started talking about last time, we had a total sum of squares, which was the difference between your observed and the mean. Oops, mean of the y's. So that's what the bar over the y means. It's the mean of all of them squared. So that's our total sum of squares. That's why we use SST for that. We're going to have an error sum of squares. Which is the difference between each approximated y value and the mean. And then you have a residual, and that is your actual difference in between computed and observed. Did I just write that backwards again? Nope, I got it right. Okay. All right. So total sum of squares, error sum of squares, residual sum of squares. So the residual sum of squares, the difference between observed and approximated, if you will, computed. This one we're not be able to get much of a handle on just because it's residual, it's unexplained error. It's this part here that we're looking for, the explained error part. So we want to try to get a handle on what the size of the SSE is relative to the size of the SST. Okay? So when we do the R squared, that ratio is SSE over SST, or the 1 minus the SSR over SST. Either way. This is a percentage of the error, the total sum of squares, that's given to us by the explained part of the model, the error sum of squares. So our goal is to try to come up with a formula for calculating basically this SSE. We talked about how we did SST last time, right? We came up with that N matrix that was the identity minus 1 over n times I times, or I guess it's iota and iota transpose. We did that matrix last time. I know it's been a week, but we did that matrix last time. And the idea behind this is that if you get to, or if you compute the y transpose, or I guess in this case, our y is the same thing as b. So let me write it that way. The b transpose times n times b, this is your SST. And remember again why that works. If you have, remember this n, basically it gives you an n minus 1 on the diagonal over n. Right? And then negative 1 over n everywhere else. Does this sound familiar at all? Okay? When you multiply that by your y1, y2 down to yn, just look at what happens in your, say in the first row times that column. You get n minus 1 over n y1, and then you get minus 1 over n times the sum of the rest of them, right? That's what would be computed in the when you take row 1 times that column. Right? I can rewrite that first part as just y1 minus 1 over n y1 minus the rest. And notice that this part right here is the mean of the y's. 1 over n times, right, this is the mean of the y's. So you get y1 minus y bar. Right? I can factor out the minus 1 over n out of both of them, and you've got the sum of the y's over n. Right? So when I take that matrix times that, I get the difference of y1 times y bar. I want to do the difference squared. That's why we put this B transpose out in front. Because remember that there were some nice properties about n that we could use. That first it was idempotent, so I could replace n with n times n. Right? And it's its own transpose, it was symmetric. Right? So we get that. So the n times b gives you the difference between each y and its mean in each component. So then you've got one going down the column, and then you got the other one going across the row now that you've taken the transpose. When you multiply them together, you get the sum of the squares of the differences. Okay. So that's why that B transpose NB gives you the SST. I mean, technically it gives you a 1-by-1 matrix that has that as its value, but you can have a 1-to-1 and onto mapping between the set of 1-by-1 matrices and real numbers. Doesn't matter. You do this, you get SST. Okay. So let's talk about how we get SSE then. All right, let's go back. I'm just going to rewrite the matrix, this N.
So is SSE SST minus SSR?
Yes. That's where I'm headed. Yep, you're right. And that's because of Pythagorean theorem ideas. It's because of the orthogonality. It's exactly why it works. Because we're doing sums of squares of things. What we have is, when you do the sums of the squares of those components, you have the square of the length of the vectors. And since it's a right angle, you have the sum of the sum of the squares of the lengths is the square of the length of the hypotenuse. That's why it works that way. You're exactly right. All right, so let's go back to this n piece. So remember, this iota is the column of ones, right? You know what the iota is? The column of ones. Okay. So what I can notice here is that if I think about doing least squares with a matrix where your A matrix is just a column of ones, okay? So think about how if you've done any of these least squares once, you've got a constant and then usually some inputs that have been computed, right? You've got that whole column of ones that's typically for just a constant term in your model, right? So no matter what you plug in for x or x squared or what have you, that constant term always just has a coefficient of 1. Right? So what if you try to do least squares and just model it with a constant function? The only thing you would have is a column matrix with a bunch of ones in it. Right? That's all you would have. So notice that this particular, I could rewrite this particular matrix as the following. I could write this as, my iota, and then I can write that times, what do I want to say? Iota, I don't know why I'm putting a prime. I want that to be transpose. Iota transpose iota inverse, and then iota transpose. notice that iota transpose iota, think about what happens. You think iota is the column matrix that just has ones, right? If I take the row matrix that just has ones and I multiply it out in front, you're taking all the ones and multiplying it by a bunch of ones and adding them all together. Well, you're going to get to n. So 1 over n can be expressed as iota transpose iota inverse. That 1 over n, this is just a scalar, so I can move it to here. That doesn't affect the matrix multiplication because it's a scalar, but I can also think of that scalar like that. All right, why did I do that? Besides torturing you. Clearly, I see pained expressions across the classroom. It looks like I'm torturing you this afternoon. Why did I do that? Let's go back up. Scroll, 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 scroll. Hey, we've done a lot today. Look at this. Doesn't this look familiar? A transpose A inverse A transpose, right? That's exactly the same form as what we have down here. That N matrix has the exact same form as what it did before, right? I'm just using iota as the A, but it's the exact same form, okay? So what does that mean for us? Well, that means that when we do this, if I take this N, I've got this as my A. I know that if I took this and multiplied it by E, what would have to happen? Well, notice that we get just what? Well, let's think about it. You would get E minus this iota, and then, now I'm going to write it as 1 over n because that's a mess, and then iota transpose times E. But what did we say that A transpose E was equal to earlier? 0, right? We agree? Okay? So this part, iota now is playing the role of A. So iota transpose times E is 0. Right? So this just becomes E again. So when I take the N matrix that we've done here and multiply it by E, I just get E. Why is that helpful? Well, good question. Everybody's asking good questions today. Good question.
How does iota work as the replacement for A? A was a specific matrix for the solution.
Right. So iota, but it depends on the form of the solution you're trying to get it to take. So iota is just, I'm saying, I'm going to approximate my data with a constant function. So then the coefficient for your constant every single time is just a 1. So that's how it works as the replacement for A in this case. It's just that in this particular case, we're thinking about it as approximating the solution with a constant. In particular, the constant you would use would be the mean. If you're going to try to approximate a bunch of data by using one value, you're going to use the mean. So that's exactly what you would get in this case. All right. So how does this help? All right, let's go back to our original model. Our B is our AX plus E. Let's just multiply through by N. Well, we just said that when we take N times E, we get E, right? I can just put E here. All right, remember our AX is our Y hat, correct? So notice again that our NB, I'm trying to get a total sum of squares here. I'm hope to split it into 2 parts, where I get an error sum of squares and a residual sum of squares. So to get to total sum of squares, I'm going to run the B transpose through on the left. So B transpose here. I now have total sum of squares on the left-hand side, right? Okay. So remember that this is let me write it this way a little bit. I can think of this as NB transpose, and then times NB. And now let's replace the NB with what we just ran through a second ago, with the NAX plus E. How do transpose works with sums? Yeah, it just goes over, right? So you just take the transpose of each piece, and how does transpose work with products? Yeah, you flip the order, right? So this would become, the first one would become X transpose A transpose N transpose, but what's N transpose equal to? N. And then plus E transpose, and then times this other part. Right? All I did was just run the transpose through the sum, correct? And forgot my arrow over my E. All right, so now let's FOIL. If I take the first term here and multiply this first term here, I'm going to get an n times an n. But what is n squared equal to? Just n, right? It was idempotent, so I get x transpose A transpose n AX, right? That's the first term, isn't it? Then we get plus X transpose A transpose NE, and then E transpose NAX plus E transpose E. I know it looks ugly, but we're almost home. All right, so let's look at the middle terms, because like I said, this looks ugly and I want some stuff to go away. Why does this look ugly in the middle? Why do I want the stuff in the middle to go away? All right, look at this one. This is B transpose NB was our total sum of squares, right? What's another name? What is another name we're using for AX? That's the Y hat, right? So this first term is Y hat transpose NY hat. That is your error sum of squares. That's SSE. And the reason for that is, remember, SSE is the difference between Y hat, each of the Y hats, and the mean of the Ys. Well, you can prove that the mean of the Y hats is the same as the mean of the Ys. So that is your error sum of squares. That's your explained part. Okay? Look at the last part. E transpose times E. Remember, your E is the difference between observed and Y hat. That's the sum of those squares when you do E transpose times E. So the last part is your SSR. Right? So we have this part on the end here is your SSR piece. So what do I want to have happen in the middle? What do I want these two terms to turn out to be? Yeah, I want it to be 0. I want it to go away. Does it go away? Well, what's NE equal to? E. What was A transpose E equal to? 0. Right? That one goes away. Now let's go here. What's true about N and its transpose? They're the same, right? So I can write that as E transpose N transpose. If I pull the transpose out, I get what? The whole thing transpose. I get NE, right? But NE is equal to E. So I get E transpose times A, which that's going to be the transpose of A transpose E. So that part will also be 0. So they both become 0. Right? There's pieces that I didn't write down. But the reason for that is because this piece is E, and A transpose E is 0. This piece right here becomes A transpose E transpose. The part that E transpose NA is the same thing as A transpose E transpose. You can work through that and get to that point. All right, so again, just to write this down, your B transpose NB is Y hat transpose NY hat plus E transpose E. So this is your SST, this is your SSE, this is your SSR. So you can get all of those pieces using the different pieces of information that we have. Okay. So let's see if we can put this to use. Let's go and play with GeoGebra a little bit. What's that?
I said GeoGebra is the slayer.
All right. So let's just make up some points here. It doesn't matter what they are. Let's say I use, let's say do 1, 4, 6, 9, and 12 for the x's, and let's say we had 3, 1, 7, -2, and 9 for the y's, and let's just see what that looks like. So there's 5 points. Doesn't look very linear or anything, so I don't know. We'll use it with a line to start with. It doesn't really matter. So remember, with our least squares solution, if I want to fit this to y equals ax plus b, say, or y equals a plus bx, whatever, it doesn't really matter, as long as you keep things straight. Then again, we want to put the x's in here, right? So your coefficients on your b will be whatever the x's are. Yeah, let's do a quadratic, just so that we can see that difference between that, because I know one of the homework problems has a quadratic in it, so why not? Okay. So we'll put the x's in, so our coefficients for the a's will all be 1s, the coefficients for the b's will be all the x's, the coefficients of c's will be all the squares of the x's, right? So when we make our matrix here, whoops, what the heck did I just do? There we go, that was weird. It was really weird. All right, so the first column will just be a bunch of 1s. The second column here will be the squares, or not the squares, just the A1.
12 changed to 11.5.
No, I didn't. I have no idea what I even did. And then here I want the A1 squared So from here now, I want to create a matrix for that, and I want to create a matrix for the outputs. And let's see if I can view algebra window. There it is. All right. So my M1 is my coefficient matrix. My M2 is my B matrix. Okay. So I want to take A transpose A inverse times A transpose times B. So I need the transpose of M1 times M1 and I need the inverse of that. And then I need to multiply that by the transpose of M1 and multiply that by M2. So those are our coefficients. So those are our coefficients for the quadratic. So if I want to make the quadratic, see if I can be clever. Nope, it doesn't like it. I don't know why it won't do what it should do. It should add those together. It just gives me the constant term. So I'm just going to type it in. So it was 4.65 is our constant term, 1.13 is our x term, and 0.11 x squared is our quadratic term. So there's our least squares quadratic, and let's see if I can get the points back on here because I lost the points, didn't I? There. So there is our least squares quadratic that fits those points. Not a great fit because, of course, those points aren't exceptionally close together. But we did ones like that last time, right? Everybody okay with how we got this set up? Yeah, go ahead.
Can you go back up to the formula for M3?
Yeah.
Expand it.
If I can grab it. There we go. Yep.
So what did you do with the M4? Nothing there?
No, I tried to get it to do the product of the two matrices, but it didn't like it.
So what did you end up doing to get the...
I just typed in the numbers.
Oh, over in the spreadsheet?
Yeah, I should be able to. I don't know why it doesn't like doing that. Let me try something else. I didn't do it in the spreadsheet. I just did it in the algebra window. I just literally typed it in. I did it up. It moved it up here. I just typed it in. I don't know why it didn't do what I wanted it to do here. Let me try something else. It didn't like that at all because it was undefined. I don't know why it doesn't like this. I'm going to try something different here. I want to force it to actually just do it as a matrix multiplication and give me the answer. Hey, there we go. There, it did it.
Why is it slightly different than your other one?
Because even though there's only two decimal places stored in or on the screen, GeoGebra actually stores more decimal places. So the second one that I did was actually more accurate than the first one. Because the first one I just typed in the two decimal places. That's why it looks different. If I go up and tell it to show more decimal places, say I do 5 decimal places, you can see that, for example, the x term here is different, and my constant's different.
So why did your I2 work? Or L2?
Why L2 worked and the other one didn't, I have no idea. I wish I did. So what I did was I forced it to be a row or a column matrix and then took its transpose and then multiplied. Because basically what I'm trying to do is take the row vector and multiply it by the column vector to make it add together correctly to get the polynomial. That's why it looks goofy. I don't know why I had to do it that way. Because if I use the older version of GeoGebra, what I did the first time will work just fine. So I have no idea why it's doing that. Might be that I have to force it to be a matrix. But I don't know why. I honestly don't know why it's doing it that way. All right. Are we okay with, besides this other stuff here, to try to get the polynomial to get formed easily? See, actually getting to that point, getting those coefficients, is that okay with everybody? Getting the formula typed in? Because now I want to do the least squares part. So remember, to get the least squares part, or the R squared part, sorry. The R squared is the SSE over the SST, right? So remember, the SSE is your y hat transpose times your n times your y hat, right? That's SSE. And your SST is your B transpose NB. So the first thing I need to do is get n in here. So probably the easiest way to do that, well, maybe it's the easiest way to do that. Let's just make, here is a column full of ones, right? So let me create that matrix. And it's referring to it as M5. So I need to, I'll even call it N, maybe. I'll even call it N and make it the 5 by 5 identity minus 1 over 5, and then it was M5 times the transpose I don't know why it's not coming up, of M5. If I can find it. There it is. There's your N matrix. The identity is a command that's built into GeoGebra. So if you type in identity of how many whatever dimension you need, and the other part, I just took the column of ones and made it a matrix, and then just did it times the row matrix of ones. So that was why I used the transpose part. All right. So if we want SST, let's do the SST part here first. The SST part is your matrix of y's, your B vector, times the n, or transpose times the n times the b. The matrix of y's is your M2 here that we typed in. So we want to do M2, oops, sorry, the transpose of M2 times the n matrix times M2. And we should get a 1 by 1 matrix, so we get 79.2. That's our SST. Right? So then we need our SSE. So we need our y hat. Y hat is A, the coefficient matrix, times the least squares solution. Right? The least squares solution was M3 here. That was the least squares solution. And the A matrix was M1. Right? So if I do M1 times the A3, that gives me the Y hat. Right? That's what we called Y hat, right? Here's my A. Here is my, where'd it go? At least, where'd it go? I lost it. Where did it go? No, it's because I clicked in the box. There it is. That was the M3. Okay. So if I want SSR here, or SSE, I mean, sorry, you want to take the A, which was in M1, and I multiply by the X, the least squares solution, which is in M3. I need the transpose of that, so I should have probably typed that in first. Okay. And then multiply that by the N, and multiply that by the M1 times M3. Why don't you enter? There it goes. So this is SSE. So if you want your R squared, then we need to take your M7 and divide it by M6. Hopefully it'll do that.
What was M3?
M3 was our least squares solution.
Scroll back up to M6. Yeah.
Okay.
What did you do to get the what did you type in to get the M3 to the equation instead of typing it in?
To get the M3 actually to come up?
Yeah, you said transpose something, right?
That part?
No, how you made it into the list, sorry. Or how you made it into L2, I think.
Oh, getting the polynomial to pop up?
Yeah, you typed in transpose and then I have to put those squiggly brackets?
Yeah, because what's supposed to happen is if you use outer brackets and then inside the outer brackets use brackets around each row, that's how you create a matrix, just by typing it in. So so the way I've got that typed in, I made a column matrix. It's got a row 1 only has one element in it, row 2 only has one element in it, row 3 only has one element in it. So I made a column matrix, but I can't do a column times a column.
Okay.
So I had to do the transpose to convert it to a row.
Okay.
Which is why I don't know why what I typed in the first time didn't work. Because I made a row matrix in that case. Should have been a row matrix.
So just type it in like that with the brackets and stuff?
Yep, that was what I did. All right. So going back down here to what we just computed, that M8 is the R squared. So what that R squared says is that 22.7% of the error is explained by the model. So it's not a very good model. But that's what the R squared tells you, is how much of the error is explained by the Y hat, which is not very much in this case. What's wrong?
Oh, I'm just trying to get the last.
Your matrix numbers are different than,
Oh,
Mine are the same as yours, but mine aren't the same as.
you tried to get like
M6
matrix
divided
of
by 5 is what we're
y.
gonna do.
Is that what it is?
Yeah, if you're doing the R squared, you just want M6 divided by 5.
Okay.
Everybody else okay with this? You get the R squared? Is it okay?
Yeah, mine's yours.
Well, of course it's not.
So what is the R squared there?
It's the percent of the error in the data that's explained by the model. So the closer it is to 1, the closer it is to 100%, the better the model is. If all of the points actually landed on the parabola, you would get 1 for this. Yeah, this is really bad. Well, I just made up numbers and then try to fit a parabola to it. Yeah, Grace.
What is our Y hat?
It's the predicted y values.
So like as far as like typing it in to get the SSE.
Oh, the y hat is this part right here. M1 times M3. So, because if you do the, here's what, if you just type in the M1 times the M3. All right. So, this, remember the x values were, I can't remember what I did, 1, 3, 7, 9, 12, is that right? It was made up.
1, 4, 6, 9.
Oh, okay. 1, 4, 6, 9, 12. Okay, so if you go up to the parabola that we formed, which was here, this is the parabola that we made. If you plug in 1, 4, 6, 9, and 12 into this parabola, you will get these 5 values. Those are the predicted y's based on the x values that are in the model. So if you plug in 1, 4, 6, 9, and 12, you'll get those, you should get those 5 numbers. If not, we did something.
So that's our y hat.
That's y hat, yes. Because our y sub i's are the actual y's that we were given. The y hat is the prediction of those y's based on the model we formed. So again, if you go through and type in 1, 4, 6, 9, and 12, you should get those values. Did it give me a function for that, or did it just make it a list? Give me an L2. So, oops. Okay, I'll just use that f of x then, yeah. So if we do f of 1, it won't be exact because I didn't use as good of numbers. But if we did f of 1, you get the 3.63, right, which is the first one. If you do f of 4, you get 1.89, but again, I didn't use that close a number, right? I used the 2 decimal approximation when I typed in the f, right? So those should be close. That's all I'm saying with that. So that M1 times M3, the A times the X, gives you predicted Y's based on our model using the same X values. That's what the Y hats are. And what we're computing here with the R squared is that, remember again, there should be, the SST is the difference, the squares are the difference from each data point from the mean of the lines. There's some sort of variance in each of your data points from the lines, the mean of the lines. What the the SSE computes is the difference between the predicted Y and the means. So again, it's another measure of variance. It's just using predicted Y's instead of actual Y's. So the ratio that we're computing is the percentage of the total variation that's explained by the model's variation. And again, the reason why we can do that is because we've split up the total variation into model variation and residual variation. So this piece is model variation. So if we divide through by the SST, it equals 1. This is the part of it that's explained, the part of the variation that's explained by the model. That's the idea. And again, there's several things about this is why it works. One is that we've split this up into these 2 components, right? And the 2 components are perpendicular to each other. So there's not any mutual variation between the 2 things. They're actually perpendicular. So each variation is independent of the other because of that perpendicularity. There's not any variance there's not any variance due to both of them varying at the same time. If the change in one doesn't affect the change in the other. But again, the reason why we can just use the percentage idea is because we've split it into two distinct parts. And this part is giving us the variance between predicted y's and the mean of the y's, versus this is actual variance in the difference between the actual y's and the mean of the y's. And in this case, it wasn't very good because it was, what, 22%? But that's what we're doing here. So we've got explained variance and then some random variance. That's what the residual part is. There's random variance in there based on whatever random events might have affected the data collection. That's the idea. But this is how we compute the R-squared. That's, by the way, that's the important part for being able to do with homework. Is that all right? All right. Yeah, Chris.
For the homework, do you want us to turn in the GeoGebra worksheet that we use?
That's fine. Yeah, that works for me. All right. Let me show you, since you're probably wondering how to do this in Excel. Yep. Okay. All right. So we have 1, 4, 6, 9, 12. And what were the outputs that I used with those?
3, 1, 7, -2, 9.
Okay. All right. So we can make up our matrix like we did before. So this is equal to A1. Pull that down. This is equal to A1 squared. And pull that down. All right. So there's our matrix A, right? Okay, so you have, it's a little clunkier to do in Excel, believe it or not, which is why I was using GeoGebra for everything, besides the point that I can graph it. So you have to use what are referred to as array functions in Excel. So here's how the array function part works. So the first thing I'm going to do is just take the transpose of this matrix. This is a 5 by 3 matrix, so it's transposable 3 by 5. So I first have to highlight a 3 by 5 area because I want the answer to appear in that area. Okay. Then the command is actually transpose. Oops. And then of course I hit the wrong button. So now I have to restart. All right. Equals transpose. All right, I want to do the transpose of this matrix. Now don't hit enter yet. You have to do it a special way. You have to tell Excel that an array function is coming. So to do that, you actually have to hit Control Shift Enter to get it to do the transpose. So you have to highlight the right size for the answer. Start typing in the command in the upper left-hand corner, and then instead of hitting enter, you hit Control Shift Enter. All right, so now we need to do a product of we have to do A transpose times A, right? All right, if I do A transpose times A, what size matrix are we going to get? It'd be 3 by 3, right? So I need to highlight off a 3 by 3 area. And the command for matrix product is M product. Ooh, it's not? Oh, what is the command then? I thought it was M product. Oh, no, it's M mult. My bad. M mult. Mult. Matrix multiplication. All right. So I use the mmult command. I highlight the first matrix, comma, and then highlight the second matrix. And then again, to get it to go, I have to hit Control Shift Enter. Okay? And then, can you see why I was using GeoGebra now? You don't have to do this in Excel if you don't want to, but I know some of you much prefer Excel to GeoGebra, so wanted to show you. All right. What's wrong?
I don't know how to do that.
Oh. Yeah, that causes a problem for you, doesn't it? All right. We can also do matrix inverse. It's the M inverse. Oh, I forgot. I gotta highlight the area first. See, this is why I don't use it. Equals M inverse of this matrix. And then I forgot, notice what I did? I forgot to hit the, it's a pain in the butt. So I don't do it. There's the matrix inverse. And then I have to do the product of this with A transpose. That's going to be a 3 by 5. And then finally, I've got to take the product of this with the column vector. So we're going to get a 3 by 1. I'll do that over here. And we get to see, we get the same answers that we got before.
What was that last matrix?
And it was multiplying that array that's in the 25 through 27 rows times the y values up at the top, the B1 through B5. That's what that one was. So you get the same answer. So, yeah.
Are we having a test on this stuff?
Yes.
Yeah. On just this topic or another one?
There will be one more topic that we'll do. I'll be a test on that too. Over the same thing, over both.
Yeah.
Yeah.
Will it be one test or two tests? Will it be on our computers?
Yes.
Okay.
You mean a Martin?
Was that
A Martin?
Martin?
Yeah. Everyone calling all work tests.
Oh, it'll be Martin. Sure, yeah, absolutely. It'll be Martin. Well, Martin. Absolutely. Yeah. So, yeah, it'll be much like the third one. I mean, basically, can you come in and do what I want you to do with it?
So it'll all be on our computer?
It'll be all on the computer.
Okay.
What's our final project? This stuff or?
They haven't decided yet.
More
Like
our
More spline? You want to do more splines?
I'm down for doing another.
Oh, we know how to do
Spline
it.
thing.
So.
Yeah, you know how to do it, so why not do it?
Yeah, so let's do it.
Yeah, it'll either be over the next thing that we talk about or the thing after that.
There are so
Two
many.
more things.
There's two more things.
How much time do we have?
Yeah, I know, we're running out of time, aren't we?
I know.
2 weeks.
And we still have that pizza.
Yeah, we still have that pizza, yeah.
And we still have to take a test.
I know.
Apparently.
How are you gonna do all this in 2 weeks? How are you gonna fit all this in?
We're gonna just stop now.
It'll be fine.
It's called France.
Yes.
Just stop. You're just done. I'm out.
Yeah.
I feel like there should be no final project.
Come on,
Final
that's our
project
final.
is being in this class.
No, it's seeing
We
if you
show
can-
up day in and day